All right, so in this video, we're going to go over the lecture we are supposed to have this week. Again, I apologize. It was not my choice to get sick. But where we left off was drawing these molecules and determining if they're polar or not. Um, so let's do that. So we have CH3OH. Let me do the Lewis structure for you here quick. And if you haven't tried these yet, please do so. All right, so we're going to look at the center carbon. I have four things attached to it, so this is tetrahedral. And we have to check if there's any polar bonds. So the two types of bonds, well, we really have three types of bonds. We have carbon to hydrogen, oxygen to hydrogen, and carbon to oxygen. So here's a little hint. Never polar, carbon to hydrogen. We can look at our electronegativity scores, which I have right here. I apologize. I was using Zoom to write. But carbon is 2.5, hydrogen is 2.1. So that is not polar. So 2.5, 2.1, difference of 0.4, not polar. Oxygen to hydrogen, that is a polar bond. Carbon to oxygen, that's a polar bond as well. And also oxygen would have this notation. All right, so this center carbon is tetrahedral. This oxygen would actually be in the bent conformation. And since we are dealing with polar bonds, let's draw this out with the bent for the oxygen. So hydrogens like that. Then we have the carbon, and we have the three hydrogens like that. Again, this carbon would be tetrahedral, but that doesn't matter because the polar bond is where the oxygen is. Let's draw our arrows. So arrows going up like that. Arrows going up like that. You add the arrows together and you add, is there a net movement of electrons? There is. There's a net movement of electrons. The arrows don't cancel out. So this is a polar molecule. Let's do SiCl4, silicon with four chlorines. So again, this is tetrahedral. We got to see if the silicon to chlorine bond is polar. So we go back to our electronegativities. Silicon is 1.8, chlorine 3.0. That is polar. So 1.8, 3.0. 3 minus 1.8 is 1.2. So that's a polar bond. And let's do the arrows. Again, we should do our geometries correctly, but this should represent what's going on good enough. All right, and I'll redraw the arrows a little bit better down here. So we have four arrows, one going to the left, one going to the right. We have an arrow going down and an arrow going up. Again, these are the flow of electrons. And you want to add all these arrows together. And when you do, they cancel out, right? The left and right arrow cancel out. The up and down arrow cancel out. So although this has polar bonds, this is actually not polar. So this is what you need to watch out for. It's not sufficient if you have polar bonds. You have to look at the way the molecules are going, the geometry and where the electrons are flowing. Next, we have CH3O, CH3. Remember, we write the hydrogens like this because we are trying to say who it's belonging to. So carbon, hydrogen, 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 oxygen, two lone pairs, carbon, hydrogen, hydrogen, hydrogen. So again, this is your bent or angular. And as we did for CH3OH, we would have the arrows going towards the oxygen. Now, if you didn't take the geometry into play, you might think, oh, this is nonpolar because what we said in C. But we have to draw this correctly. Which is like this. All right. And so when we do that, we have an arrow going to the oxygen, we have an arrow going to the oxygen, and hey, all the arrows do add up for a dipole. That's what we're drawing. These are called dipoles. You don't really need to worry about that too much, but if you take more chemistry, especially organic, you're going to hear that word. Dipole just means we have a positive end and a negative end, which we do here. And so CH3OH, OCH3 is polar, right? And if you need more examples that I should have put more in the worksheets, feel free to email me if you have questions about that. But we are going to move on to the last thing you need to know for your test next week. Let's get rid of these drawings, and I'm going to go back to drawing with Microsoft Edge. So we have two things we need to know. First are resonance structures. So briefly, when you're doing a Lewis structure, so we have ozone here, it's possible to make two different Lewis structures. One, we can have where we have a double bond going from the left to the center oxygen. The second one is where we have a double bond going from the center to the right. In reality, neither of these is correct. Rather, it's a hybrid of the two, right? And so a hybrid, we have an example here with dogs. I have two dogs. When they mate, they create a dog that's like half and half of each. You might also know that from hybrid cars, if I know how to spell here, hybrid cars. Hybrid cars use both gas and electric. So for chemistry, a hybrid structure is when you have two Lewis structures and you combine them to make one. And so let's take a look at this terminology here. So we have a line dot dot dot. That dot 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 means partial double bond. That means it's almost a double bond, right? It basically means the double bond is not permanent. And honestly, that's not the best way I could say that, but it's a good way to begin with. What you can think of is that since we have two Lewis structures, you can think that we bounce between the two. Like this double bond will switch left and right, left and right, left and right, left and right. But as I have here, it doesn't actually do that in reality. In reality, this is more like a 1.5 bond, right? It's not a single bond, it's not a double bond, but it's between the two because you have these resonance structures. And so when we look at the real Lewis structure, we have to consider any resonance structures we can have and say, okay, well, it's a mixture of the two. That's what's really going on there. And so let's say we do make multiple resonance structures. And I want to know, are they equally good or is one better than the other? And if one is better than the other, that's usually the real structure. All right, so let me just write that down. If you make multiple resonant Lewis structures rather, remember, we call these resonance structures. When you make multiple Lewis structures, they are resonance structures. If you make multiple resonance structures, we need to score them. And there's two outcomes. Outcome number one, your resonance structure have equal scores. If they have equal scores, that's when you have that hybrid molecule that we talked about in the previous slide. Option number two, unequal scores. Then really, if you have two Lewis structures, two resonance structures, and they don't have the same score, then one Lewis structure is better, and that's the one you pick. And we're going to do examples of this, and I'm going to tell you about the scoring system. I just want to lay that groundwork, all right? So when I'm making multiple resonance structures, I need to assign them a score. They have equal scores, I will combine them to a hybrid. If they don't have equal scores, I just pick one and say, you're the real one. So what is this scoring thing? Well, that's the title of our slide, formal charge, right? And the lower the formal charge, and lower is actually not a great word. So let me fix that. Closer to zero. That's better. Closer to zero, the formal charge, the better Lewis structure. So generally, we want things that have a formal charge of zero. That's how we know if they're good. So how do I score this? It's an easy formula. So it's the number of valence electrons minus the number of non-binding electrons. This is lone pairs. Minus 1/2 bonding electrons. This is weird way they say it. So the way I would say it is minus number of bonds. And by number of bonds, a single bond gets a score of 1. A double bond gets a score of 2. A triple gets a score of 3. So you're going to take the number of valence electrons minus how many lone pair electrons you have minus how many bonds. So let's take a look. We have two structures here in this table. So I've just bracketed them so we can look at the two structures. And I want to know which structure has the better formal charge, which Lewis structure is correct. So hydrogen has 1 valence electrons. In this structure, no lone pairs. We have 1 bond, 1 minus 0 minus 1 is 0. That's generally what you want. Carbon, 4 valence electrons, no lone pairs, but it has 4 bonds, so that has a score of 0. Nitrogen, 5 valence electrons. It has a lone pair, so minus 2 for the 2 lone pair electrons. And it has 3 bonds, minus 3, 0. All right, so that's what you're looking for. So this is a great Lewis structure. However, let's say we switch the nitrogen and the carbon. What would happen? So hydrogen doesn't change, but nitrogen starts off with 5, no lone pairs now, 4 bonds. It has a score of +1. Carbon, 4 valence electrons, 2 lone pairs, 3 bonds, score of -1. So this is not as good. So if I was comparing the left to the right, since the left has more zeros, I would pick that as my Lewis structure. But again, if we had the same scores, then I would combine my Lewis structures to make a hybrid structure. So here's how we do our scoring. Better structures have fewer formal charges. Better structures have smaller formal charges. So if you do have formal charges in both, the smaller numbers are better. And better structures have the negative formal charges on your more electronegative atom. You can have non-zeros, right? You can have non-zero formal charge and be okay. Like that can be a fine structure. But we have to make sure any negative charge is on our electronegative atom. So here's a question. I want you to try this out. I have 2 examples here. I want to know left and right in A, what is the better Lewis structure? Left and right in B, what's the better Lewis structure? Use formal charges, right? Even if you can just look at this and see, use formal charges. I want you to pause the video and try this because your test is next week and this is material that will be on it. But I'm going to go through it right now. So yeah, if you haven't done it yet, please try so. But we're going to call this left A and right A. left B, and right B. So left A, we have hydrogen. The hydrogens are the same, so I'm only going to do that for one of them, carbon and sulfur. So number of valence electrons in hydrogen is 1, carbon is 4, sulfur is 6. No lone pairs on hydrogen, no lone pairs on carbon, 4 on sulfur. 1 bond for the hydrogen. And remember, these are individual hydrogens, but they're the same here, so I'm only doing 1. Minus 4 bonds for carbon, minus 2 bonds for sulfur. So our scores are 0, 0, and 0. So left A is probably going to win, but we could have the same scores. So let's do right A. We're going to do the same thing. HCS. So hydrogen 1, carbon 4. These are our valence electrons, right? Hydrogen has no lone pairs. Carbon in the right has 4 lone pairs. Sulfur has 0. 1 bond for the hydrogen. 2 bonds for the carbon. 4 for the sulfur. So our scores are 0, minus 2, plus 2. So the better structure of the two is left A. Let's do left B versus right B. Same idea, except we are adding another hydrogen. So let's do left B. And again, all the hydrogens only have 1 bond, so they're the same. So I'm just going to do HCS, 1, 4, 6 valence electrons. No lone pairs. No lone pairs for carbon. 2 for sulfur. 1 bond for hydrogen. 4 for carbon. 3 for sulfur. And so we have the score of 0. Carbon has a score of 0. Sulfur has a score of +1. All right, now let's do right B. Hydrogen, carbon, sulfur. 1, 4, 6 valence electrons. Hydrogen, no lone pairs. Carbon, 2 electrons in the lone pair. No lone pair for sulfur. Hydrogen, 1 bond. Carbon, 3 bonds. Sulfur, 4 bonds. So our scores are 0, -1, and +2. All right, so your winner here, the better structure, is left B. Why? 1, on the right, I have 2 atoms for the formal charge. You generally don't want that, versus 1 atom. Also, carbon's not very electronegative, and we have a minus charge on it. So carbon usually doesn't want it, but you could have just decided from the formal charges. All right. So with that, we're going to get into our last topic here. Valence bond theory. How are we making these bonds? And so the first thing we are going to look at is a very simple case, making H2S. And basically, one way we can think about it is that we have half-filled orbitals, and these orbitals overlap with each other, right? So in H2S, hydrogen is 1s1, and sulfur is 3s2, 3p4. When we do our electron diagrams, right? Sulfur can put 2 electrons in its p orbital, and then hydrogen can put 2 electrons in its, or 1 electron in each of its s orbital. So that's how we first think about what's going on. We have an s orbital, the 1s orbital in hydrogen, overlapping with the 3p orbital in sulfur. And since they're sharing electrons, right? Since they share electrons, we can think, okay, well, you are now full because you are each renting an electron from each other. So that's the first way we kind of think about bonding. We can't bond with the orbitals that are already full. right? They can only have 2 electrons in those boxes. So those will not bond at all. However, that does not explain most bonding. For example, let's say I said make a structure between carbon and hydrogen. And if we did that, what you might think is looking at carbon, carbon is 2s2, 2p2. It has 2 half-filled orbitals. Hydrogen has 1. So imagine I make another 1. So you might think the structure should be CH2, right? 1 electron goes in this orbital, 1 electron goes in that orbital. But that is wrong. That will not happen. What will happen is CH4, which is tetrahedral here. So we need a new way to think about what our orbitals do when atoms bond to each other. Now bring us to the concept of hybrids. A hybrid orbital is when you have your orbitals combined to make new orbitals. And the important thing is you have to have the same number of orbitals when you make a hybrid, right? You can't make new orbitals. You can't delete orbitals. What I mean by that is that carbon right here has 5 orbitals. Remember, each box is an orbital. So when I make my hybrids, I still need 5 boxes. Or sorry, 4 boxes. 4 boxes. 1, 2, 3, 4. For this hybrid orbital theory, to keep it simple, we're only going to look at center atoms. All right, so let's take a look at how we do this. We're going to start with the hybrid that's called sp3. All right, so this is carbon bonding with 4 hydrogens. What is happening for that carbon, you're going to combine all your valence orbitals and you'll make a new orbital. So you're going to combine your s and your 3 p's to make sp3. That's where the name comes from, right? I have 1 s orbital that is mixing with the 3 p orbitals. We now have a hybrid called sp3. I have pictures going on here about what these orbitals look like. You don't need to worry about that. All right, you're not gonna draw this stuff for me. What you need to know is that if I bond 4 things, so if I have 4 electron groups, because this works for lone pairs too, my hybrid orbital is called sp3. That's what you need to know. If I bind 3 things, whoa, there goes my voice. If I bind 3 things, then we call an sp2 orbital. So I'm going to combine 2 p's and 1 s, right? And we can look at this for H2CO. H2CO has this Lewis structure. I have 3 groups, 1, 2, 3. So basically I'm combining 3 orbitals to make a new orbital, and I have a p orbital just hanging out by itself. If I have 2 groups, then it's sp. I combine 1 s and 1 p. So CH2 is our example here. So 1, 2, 1, 2. So I take 1 s, 1 p, and make my hybrid. And that's what we're overlapping here. I know I'm going through this kind of fast because this table, this is what you need to know. If you have 2 electron groups, you're sp. You have 3 electron groups, you're sp2. 4, sp3. 5, sp3d. 6, sp3d2. So it's a counting game. right? Starts at SP, and every time you go up, you add a number to P, so SP2, SP3. Remember, P can only have 3 orbitals, right? Because P has an L value of 1. So m's of L is -1, 0, +1. Remember, that's how we get these boxes. So once I go past sp3, I need to bring in the d orbital, sp3d, sp3d2. So that's what I would like you to know for our test. If I give you a structure, tell me the center atom, what hybrid orbitals could it have? Of course, we're going to do an exercise with that. I'm going to walk you through CO2. So step 1, draw the Lewis structure. For CO2, it looks like that. All right. Then you count how many groups. So we have 1, 2 groups. If you have 2 groups, that is called SP. Another way to remember this is like all the numbers should add up to how many groups you have, right? Because S is 1, P is 1, 1 plus 1 equals 2. Oh, I have 2 groups. That's what I need. So pause the video, take some moments, give me my Lewis structures, tell me what the hybrid orbital is in the center. I'm going to go through them right now. But again, if you haven't tried them yet, please pause and do so. Let's do BR3. So BR F3. So BR has 7 valence electrons. 1, 2, 3, 4, 5, 6, 7. So that's a Lewis structure. BR has 5 groups. So S, remember that's 1 group. We can have a maximum of 3 for P. So that's 3. So I need to bring in another one, which is D. Hey, I have my 5 groups now. So the hybrid orbital that bromine is making is sp3d. Now we have CH3, CHO. And I'm going to do this for each carbon. All right. So carbon on the left has 4 groups. So this would be sp3. The S is 1, the P is 3. 1 plus 3 is 4. Carbon here, I have 3 groups. That would be sp2. S is 1, P is 2, 1 plus 2 is 3. So hybrid orbitals are actually really complex because of all the shapes you're making. But for general chemistry, we are just going to keep it simple and we're going to look at the hybrids we make. When you get to organic chemistry, then it might become a little more complicated for you. But that's all I have. That's all you need for test 4. If you have any questions whatsoever, let me know by email. Otherwise, I will see you folks next week. Hopefully I don't get sick because I am traveling again. So we'll see. We'll see how my luck goes. Bring me some pie. Just kidding. Don't do that because I will eat it. Otherwise, see you next week.